Okay, folks, sorry that I'm not there today. Um, this is not like the worst lesson that we've had though, so it should be okay for you guys to figure out on your own as long as you follow along with the video. Today should be November 22nd for all of you. And the first job here is to write three possible equations for the graph shown. The problem is the axes aren't labeled very well, and I don't really want you to get too crazy with transformations, so I'm going to kind of adapt them so that they fit. So that we don't have to worry about putting all kinds of transformations into things. Okay, so I don't love the way that this is drawn, but let's just assume that we don't have anything too crazy happening with anything. So then that would be negative pi by 2, and this would be negative pi. Okay, so I don't want anything too kooky going on with your transformations there. I just want you to come up with three equations that could represent this, assuming that it is a sine or a cosine function that has not been transformed much. Okay, so mute or pause me, take a second, come up with three equations, and then come on back and I'll write down a few. There's like an infinite number of them. So you go ahead and do that. And if you're back, the first one that I would see, assuming there's been no transformations, like I just kind of tried to make clear, would be like negative sine, right? So instead of going up, it comes down and up. So one option here might be like y equals negative sine x. Okay, so that would be your sine wave reflected. From your test yesterday, you saw this, well, one group of you saw this. It could also be the sine of negative x, so like regular sine reflected over the y-axis, or the x-axis is going to produce the same thing. And that's that odd symmetry that it has. So this is just kind of reversed from what a regular sine wave would look like. If you really wanted to use cos, this could be like your starting point. So you might have said y equals cos x plus pi by 2. Okay, or I guess you could have gone right to 3 pi by 2 as well. So there's all kinds of options. Okay, there's an infinite number of things you could write, especially when the scale wasn't labeled at all. Okay, now that it has some numbers on it, at least you have some reference points to work with. But that was kind of what you're looking for there. And we're talking more about that idea of equivalence. And a lot of you guys had a really hard time with the idea of stating that two trig kind of equations are equivalent to one another, or trig expressions, on the test and in the homework, and I took up a bunch. I think the thing that you struggle with is that there's no math. Like for you to tell me that negative sine x is equal to the sine of negative x, you need to actually understand the graph. You can't just plug it into a calculator. And I think that happened on your test a lot yesterday when you guys had a random angle and you had to identify the acute angle and then figure out if the sine or the cosine would be the same or the opposite sign. Like some of you were telling me that sine and tan were equal. They're not, right? Because the ratio is going to be different because you're putting different sides into it. Okay, so down here I'm just kind of summing up for you guys. Because trig functions are periodic, there's always multiple correct answers when you are asked to write an expression or an equation, unless you are given specific parameters. Okay, so we can use graphs to check for equivalence using Desmos. So if you think that you've written two things that are equal to one another, you can put them into Desmos, and we'll actually use this for trig identities. And you're going to see if you get one graph or two, right? So if they both create the same graph, then that means that they're equivalent. If not, that means something went wrong in your proof. Okay? In the event that you have functions that aren't too complicated, you can graph by hand to see if they're equivalent, right? So the example I have here is like your most basic. So if you have graphs of sine x and cos x, you can look and be like, okay, I can transform the graph of sine x to create an equivalent function to y equals cos x, right? So if I want to move this graph to be on top of that one, I have to go that way pi by 2 units or radians along the x-axis. So to state that as equivalent expressions, I would say that cos x is equal to sine x plus pi by 2. Okay? So that would be one equation. And I mean, you could, I guess, move it from here. So you could move it all the way over from, which one am I looking for? Like way out there. You could bring that over. You could reflect and shift. This is the most simple way to make sine into cosine though, right? Shift sideways, pi by 2. You could also come from here and like flip it up and move it to the right. I don't know. You got lots of options, but this is what I mean by right expressions that are equivalent to one another. Okay, so those are equivalent to each other because they would produce the exact same graph. Okay, and notice no math, no calculator, no degrees, nothing, just looking at the picture and thinking about transformations. Okay, so I know a lot of you guys are tired of graphing, you don't love graphing. We can avoid graphing using what we know about the behavior of trig functions to identify the ones that are equivalent. So because they're periodic, there's some tricks we can use. Okay, and I will not torment you with my bad handwriting. I will just do that. There we go. Okay, so the things that we can do, and again, don't try to memorize this, just have it as kind of a checklist for yourself and practice it until it becomes kind of second nature. So you can do horizontal translations by multiples of the period to give you the exact same graph again, right? So if I take a cycle of sine x and I shift it 2 pi units, it looks exactly the same because it's periodic, so every period repeats itself. So that would be something like, oh, I don't have a pen. There we go. So like sine x is going to be equal to, I get out of practice with this little tablet, thankfully, because we're not online, but it makes it the worst to write with. There. Okay, so if I shifted sine to the right 2 pi, you can't tell I shifted it. I didn't do anything productive. Horizontal translations of pi by 2 to the right of a cosine function will give you sine. Okay, and we just looked at how moving sine to the left, pi by 2 will give you cosine. So that's just the opposite of what we just did. Horizontal translation of a sine function pi by 2 units left will give you the equivalent expression. So those are the two that we just kind of looked at with the graph. When you reflect y equals cos x across the y-axis, you get the exact same thing. And this was a test question on one of the tests, okay? So this has to do with even symmetry for cos. So cos x is equal to cos negative x, because if you take this graph as best as I can and you reflect it over the y-axis, it's just going to continue that graph. Okay, so those are equivalent statements. And then we know that our sine and tan functions, well, you might not have known that tan was odd, but now if you go back and look at it, you'll see that it is. The sine and tan functions are odd, so they have that symmetry around the origin. So you get the same graph when you reflect over x or y. So that means that like sine negative x is equal to negative sine x. And that was on the other test. So if you didn't have cosine, you had sine. And the same would be true for tan. Okay, and that's going to come in handy when we're doing identities, because that way you can rewrite something that has a negative in it with the negative outside, or as a positive, and it's going to help you to prove that sides are equal and things like that. But this all makes sense because of transformations. Okay, so if I have the graph of sine, oh, how about if I draw actual sine? So if I have a graph of sine that looks like that and I reflect it in either direction, so if I reflect over x, it looks like that, and if I reflect over y, it looks like that, and that's all one graph. So those two produce the same picture, and tan does the same thing because it's a lot like kind of a cubic function right around the origin there. So it's similar to like an x cubed scenario. Okay. And then the last kind of way for us to think about equivalent expressions that is new, and then we'll talk about a review of the thing that was on the test. We can think about equivalent expressions using triangles. Okay, so this isn't one that we've talked about too much, but this is where you would start comparing sine to cos and tan to cotangent. So I don't know if some of you had watched some YouTube videos and that's why you thought that was okay yesterday. But this is where that actually comes in. I will ask you very specifically to use cofunction identities to write an equivalent statement. So make sure you know what the heck cofunction identities are. And I'm about to show you, okay? So in any right triangle, remember I'm going to talk in radians, but it's the same deal as degrees. The two acute angles, so these two angles, have to add up to 90 degrees or pi by 2, right? Because this is already taking away pi by 2, and the total sum of your angles is pi. So sum of angles equals pi. That guy there is pi by 2. So all that's left for the two acute angles is pi by 2. So my two acute angles add to pi by 2 as well. Okay, so 90 there, 90 here. So that means one of them can be called theta, and then the other one is going to be pi by 2 minus theta, because it's whatever's left of that piece that you have. Okay, so now we're going to kind of derive our cofunction identities using things that we know. Okay, so if I'm talking about theta, so let's label relative to theta, and we're going to go back to grade 10. That's going to be my opposite, right? This is always going to be my hypotenuse, and this guy is going to be the adjacent. But if I label my sides relative to this guy, that becomes my opposite, and this one is my adjacent. Okay, so those two sides switch. Okay, so my sine of theta would be opposite over hypotenuse. But those same two sides, if I look at this angle, are actually the cos. Okay, so the sine of theta is equivalent to the cos of pi by 2 minus theta. Okay, because I'm using the same two sides, so I'm using this side and this side in both of those ratios. Okay, and then my cos of theta, so again, adjacent over hypotenuse, the adjacent and the opposite switch, is going to be equivalent to my sine of pi by 2 minus theta. Okay, so that's what cofunction identities are. And then when we're talking about tan, it's a little weirder. So the tan of theta is opposite over adjacent. And then when we talk about pi by 2 minus theta, those two sides become the adjacent and the opposite. So it's actually just the reciprocal of tan. So cotangent of pi by 2 minus theta. And of course, when I ask you about these, I'm not just going to ask you to use them, I'm going to ask you to explain them. So make sure you can see clearly that like you switch the opposite and adjacent sides, so it switches the ratio, but it also changes the angle. You're not telling me the sine of an angle is equal to the cos of the same angle. You're telling me the sine of an angle is equal to the cos of the remaining angle in the triangle. Okay, so those together are your cofunction identities. Okay, and that would just be if you're working in a right triangle. Okay, and then the other thing that we can do is apply the cast rule and the things that we've done in the last chapter. So we're going to still do exactly like that test question, exactly like the stuff from 6.2 to keep working on these two equivalent expressions in terms of the related acute angle and all of that good stuff. So if you want to write two, so we're going to write two different equivalent expressions for the cos of 5 pi by 6. Step one is going to be to draw 5 pi by 6. Ooh, or not. Okay, so remember we have 0. This would be 6 pi by 6. This guy here would be 3 pi by 6. So 5 pi by 6 is over here. Okay, and then the cos of 5 pi by 6, because I'm in quadrant 2, is negative. Okay, so this value is negative. So I'm going to write down all my thinking because there was a lot of struggle with this question. The related acute angle right here is pi over 6. Okay, so beta is pi over 6. So I'm going to draw that all on its own. Okay, so there's pi over 6 in quadrant 1. The cos of pi over 6, just the regular acute angle in quadrant 1, is positive. Okay, so these two things have opposite signs. So if I want to write them as equivalent, and I'm not worried about the numbers, I don't care what the values are, I do know this though. I know that the cos of 5 pi over 6 is going to be equal to the opposite of the cos of pi over 6. Okay, so that's option 1. So that's my first set of equivalent statements because cos pi by 6 is a positive number, cos 5 pi by 6 is going to be the same value but negative. So I need a sign indicating that those two have opposite signs. Okay, so same absolute value, I guess. Let's do that. Opposite signs. So that's what I'm indicating when I write that. Okay. Now the other thing to think about is what quadrant is cosine also negative in? Okay, so if I have to come up with a second one, I'm going to go, okay, cos is also negative in quadrant 3. Okay, so I'll come over here. Right, I'm going to come into quadrant 3. So I have this angle, which is going to be pi plus pi over 6, because that's just my related acute angle right there. So that's going to be 7 pi by 6. Okay, so that shares the same related acute angle as this one above. Some of you guys thought that would also make a right triangle. It totally doesn't. It makes an isosceles triangle, I guess, if you connect all the things. But it's not a right, or it's not a right isosceles right triangle there. Okay, so pi by 6 would be like here. This is 7 pi by 6. Those two angles would have the same cosine ratio because they are both negative. Okay, so this value is negative. So the other option here is to say that the cos of 5 pi by 6 is exactly the same as the cos of 7 pi by 6. And then the third option would be to talk about 11 pi by 6, and it would be positive, so it would be just like this. So it would be cos 5 pi by 6 is equal to negative cos 11 pi by 6. Okay, so again, when you're doing those, I'm not looking for you to calculate anything. I'm just looking for you to understand how that related acute angle kind of moves itself around from quadrant to quadrant, and how the signs change without the values changing. All right, there's a couple of practice problems. I would suggest, again, pausing and then trying them and then coming back and checking out my answers when you're done. So you can go ahead and do that, and then I will walk through these with you. Okay, so for number 1, when it says to use the cofunction identities to write an expression that's equivalent to the cos of 5 pi over 12, I would say draw a triangle. So you know the cofunction identities belong inside of a triangle. So my first step here is going to be to just draw this. Okay, because I know right here is pi over 2. And then I'm going to call this here 5 pi over 12. Okay, and then this is going to be my missing angle. So the first thing you do is draw it. The second thing we're going to do is find theta. So we know that these two things add up to pi by 2. Okay, so here's what I know. I know that theta plus 5 pi over 12 is going to equal pi over 2. Okay, so to get theta, I'm going to write this with a 12 as a denominator. So I'm going to have 6 pi by 12 minus 5 pi by 12. And that's going to give me pi over 12 as my measure for theta. For anyone who is struggling with this with calculators, leave the pi out. So you're really just doing 6/12 minus 5/12 to get 1/12 because the pi is common to both. It's like adding like terms. You don't try to type x into your calculator ever. So why would you want to try to type pi in? So there's my answer for theta. Now I know this to be true. So pick an identity and no one panic. These are not like hardcore trig identities here. I know that the sine of theta is equivalent to the cos of pi over 2 minus theta. So using the numbers from the question, use these values. I know that the sine, oh, hold on. They want me to use cos, not sine. There. Okay, so I know the cos of the angle that they gave me is equal to the sine of pi over 2 minus theta. And then that means that here I would say the cos of 5 pi over 12 is the same as the sine of pi over 12. Okay, so I don't care what the side lengths would be labeled as. I just know that the cos of this would be like this side over this side, right? So that's cos. But then for this angle, those same two sides create sine. Okay, so I would be using the same two sides in that expression. The other thing I think some of you are struggling with is the concept that your angles are now fractions. This is not a ratio. This is not telling me anything about side lengths. Pi by 12 is an angle. So you cannot draw a triangle and label one side as pi and one side as 12. That's not right. That's an angle measure, okay? You would have never taken like 30 degrees and put 30 on the opposite and 1 on the hypotenuse. And that's what you're doing if you're trying to label triangles using the pi and the number. Okay, last one was write an expression that's equivalent to the sine of 7 pi over 6 using the related acute angle. So again, draw it. This was 6 pi over 6 2 seconds ago. So that makes this 7 pi over 6 over 6. And then that little related acute angle in there is pi over 6. And you can draw that in any quadrant that you'd like. And again, I tend to default back to the first one, but I know that over here, sine is negative because y is negative, and up here, sine is positive. So the easiest way to go for me is just to say the sine of 7 pi by 6 is the opposite of sine pi over 6. Okay. Another option for you would be to go here, right? So 11 pi by 6, sine is also negative here. So you could say the sine of 7 pi by 6 is exactly the same as the sine of 11 pi over 6. But I'm not looking for the numbers. I'm just looking for you to understand the concept of equivalence, so the ratios would be the same for both of those because the triangle is the same, right? Like this right triangle here and this one would have the same measurements and side lengths in y and r. They would both have a negative y and a positive r. Okay? So hopefully that makes some sense and it wasn't anything too new or groundbreaking. From there, I want you guys to go and try the homework. Once that's done, you can correct your test. And then tomorrow we will move on to kind of some new fun tricks with properties of trig functions.